Speaking about YouTube, hello guys over there. If you want to interact with us, you can. I'll read your chat.
Yeah, I'm a little bit scared, of getting owned.
Are you scared?
Yeah,
What?
in case I could get owned, I could talk some shit and somebody
Owned?
contradicts me.
No.
Yeah,
Oh, I thought you said getting
normal.
old.
Yeah,
Yeah.
just like getting contradicted with facts.
You
Don't
mean-
talk. The best thing
Yeah.
for you to do is just keep your mouth shut forever. That's the way I look at it.
Yeah, that's what I was thinking,
There's a saying: it's better to be thought a fool than to open your mouth and to prove it.
Like maybe they will clip me, they will upload me to YouTube, and I look like a fool.
Yeah. Well,
You're
I
doing
can
it
ask-
right now.
Yeah, that's already happening in real time. That's right.
You mean PWN too, right?
PWM. What is it?
That's lead
Why don't-
talk.
Why don't you just tell us how you know the Earth is a?
He doesn't know. He doesn't know what that means. Come on now.
Yeah. Not really.
Hey Tommy,
Yeah.
let me ask you.
Give away our secrets.
Can I ask him a couple of questions, guys?
Oh yeah.
All right, let me see this. Tommy, are you able to watch the chat?
Yes.
All right, I'm going to post one picture for you, and I want to ask you a couple of two questions about it.
Okay.
Let me scroll here. And this is kind of fun because we do this a lot, and people sometimes they can answer it, sometimes they don't. So if you don't worry about it, if you can't answer it, you haven't been owned. Okay.
I don't think I've ever seen this one. I'm curious. Is it better than Radwin's?
Yeah, it's about the same. All right. Do you see the picture in the chat?
Okay, yeah, it's about the same.
Yes. An Earth's picture.
Yeah, it's a picture of Earth, right? It's at least the way they tell us. They say we live on this ball in space. Agree?
Yeah, pretty much.
That's the story. Do you know all the blue stuff in that picture? Do you know what it is?
That's ocean.
Yeah, it's water.
Yeah.
Do you notice something funny about the water in the picture? Like peculiar, something weird.
Not really. No.
It curves around the ball. Right? That's a little
Yeah,
bit
but
weird.
that's because it's like illustrative. It's not like a real photo, or it's at least like edited.
Well, they say they say this is what the Earth looks like, and it has curving water on it. That's what they say. NASA, for example, right? They send us
Sure.
pictures. They send us
Yeah, but
pictures
isn't
from
like
space.
all of that curved? Like not only the water, but the entire thing.
Yeah,
is-
everything is curved, but Earth has a lot of water on it, so most of it is water covering the surface, right? Do you happen to know the Earth's radius? That's my second question. Because you answered the
the
first one correct. It was water. The
I
second
think
one is
if you in kilometers, I think it's like around 18 kilometers, maybe. Maybe it's less.
it's actually 6,300 something
Okay, yeah, a
kilometers.
lot less. Yeah.
Yeah, the radius, right? So and I'm in America, so I do it in miles. In miles, it's 3,959
You
miles.
can see it, yeah.
Yeah, you can even see it there. Yeah, there's some text. So because we know the size, right? We can figure out with math how much water needs to curve over distance. You understand? You with me, right?
Yes, of
You
course.
can easily figure it out. So if you look in the diagram, if Earth has a radius of 3,959 miles, over 10 miles, it has to curve 66 foot. That's just math. It's in logic. You agree?
Yes, it's a fact.
Yeah. It's exactly. Yeah, it is. It is. So here's the thing. They do send us a lot of these pictures. They call them pictures, right? Or images from space. And they say, this is where you live. You live on this ball. This is the size, and water is curving on it. So I thought about this a few years ago, and I was like, okay, great. I mean, really? How can I confirm this myself? So I did the math and I went out to a lake, and you can do this as well. Anybody can. So you don't even have to believe me. But if you shoot the laser 30 centimeters over the water, over a 10-mile wide lake, it has to end up 66 foot in the air on the other side. If we live on a ball, you agree, right? If we
Yeah.
live on a ball, yeah. The thing is, when you shoot that laser, it's going to end up 30 centimeters over the water on the other side as well. Because guess what? Water does not curve. So I can't confirm these pictures. That's kind of weird, right?
Well, but when you say they, what do you mean by they?
I mean, anyone who makes the claim, this is the mainstream claim that we live on a ball that's 3,950 miles. That's the radius. So water has to curve. 66 foot is like a 6-story high building, or 20 meters. Are you in the metric system, or do you like the
I
imperial?
use meters. I don't use.
Yeah, me too. I'm from Sweden actually, but I lived in the States for a long time, so I use both, right? But 16 kilometers has to curve 20 meters. That's like a 6-story high building. So you could take your friend right now, go to a lake that's 16 kilometers wide. Have your friend stand on the other beach and get a good camera and see if you can see him from your side, right? And I mean, unless your friend is 20 meters tall, you should not be able to see him because there is curvature, you know, between you if you live on a
Okay.
ball.
Okay, so can you say it again?
Yeah, if you take your friend to a 16-kilometer wide lake and you get a zoom camera and you can zoom in and see him on the other side, well, either your friend is 20 meters tall or there is no curvature on that water. You
Yeah, that
understand?
makes total. Yeah, makes sense.
Yeah, I mean, that's what it is. So it's so weird that they say that the Earth is a ball, because when we go out and actually test it, and we do laser tests. Here is I can paste the laser test in the chat if you want to look at it at your convenience, right? These guys took laser to a 21-mile wide lake out in
Yeah.
Utah, and they shot laser over it from one side to the other. And it was 5 foot on one side, and it ended up 5 foot on the other side. It
Yeah.
should have ended up almost 100 meters in the air, but it doesn't because, well, water doesn't curve. So,
Yeah, so
huh? Isn't that interesting?
yeah, I actually looked it up. Here it says that the Earth's curvature, like over 16 kilometers, it creates about 20 meters of drop
Yeah,
relative to a tangent.
I know. It's
Okay.
super weird. And we can't find that. We tried, we've done thousands of these tests. I pasted one in the chat, and there is like, I mean, if you talk to anyone here, we can paste hundreds of these, right? So, just something to think about.
And why are they hiding it?
I don't know if they are hiding it. I just don't think that they're thinking about it. I mean, most people just believe what their teacher in third grade told them, right? I mean, when we were like 9, 10 years old, they put this globe in front of us and they said, hey, this is where you live. And when you look at YouTube or all the cartoons, they tell us we're in space, right? And we're on this big ball. And I mean, somebody just told them it's basically tradition at this point. Nobody looks into it. Nobody goes out and do these tests, except for a few people, like me, for example, and the other people in this channel.
Right. Yes, sir.
So yeah,
Yeah,
it's
but I mean, like, what about all the different, like, what do you call them? Like, you have radars and like different stuff that are based on uh curvature, right? They are based on a
well,
round Earth.
that's interesting you should say that, because actually those things like radar, we can shoot radar signals 1,000 miles. I mean, we did these kind of tests. We shot radio waves in the 1800s, 10,000 miles, like from England to Australia. That would not work on a ball. It only works over a flat surface like the ocean, right? So,
Yeah, no, I
uh,
want to say something about the radar thing real quick.
yeah, go
The
ahead.
Australians just built, well, I'd say just built, like within the last 30 years. It's called the Jindalee radar system, which is a quote unquote over the horizon radar. They said that they can, from Australia, pick up on radar airplanes in North Korea. This is what they say, according to which is supposed to be 4,600 kilometers. So do with that information what you want.
And what about planes?
What
Like,
about it?
planes, they when they travel, they fly, they don't do it like in a straight line, right? They use like a curved path.
Oh, do you want me to handle it? So I can only talk for like a couple of minutes because I gotta go. But
Sure.
they don't actually fly in a curved path. That's just projecting onto like a Mercator map. So where the way planes actually fly in reality is there's these things called international or domestic flight corridors that all the planes fly in. So like all cross Atlantic traffic in the north flies in the corridor, all the stuff in the middle flies in another one, all the stuff in the south flies in another one. The same with the Pacific. They have flight corridors that airplanes fly in. They're not curved. They're not curved paths. The curved path is just because they're showing it on a particular type of map. But if you can show it, I could actually post it in the chat. Like I could post a map showing an airplane while they're in the cockpit. So it's the pilots in the cockpit looking at their flight chart that shows them traveling in a straight path. But the only reason it shows them traveling in a straight path is because it's a polar projection. So it's a different type of map, and different types of map will make the path look different depending on the type of map.
Okay, gotcha.
But I want to go back real quick to what you said. Like, why are they hiding it? It's not hidden. The Earth, like, you can't hide the flat Earth. It's not hidden. It can't be hidden. You're just giving an alternative version of reality, and you chose to believe it. It's not hidden at all.
Well, it's like it's pretty much hidden as much as like anything that.
No, they're just giving you false information. That's it. If the Earth looks flat and you don't feel it moving, how can they hide that?
But who are they? That's the question. Who are they?
That's my question. You said, how are they hiding it? It can't be hidden at all.
Okay, but
It's not
okay,
being
let's say
hidden. You're just
okay,
being given an alternate story. So,
let's
like, listen, Tommy, if you tell somebody, hey, Earth is a globe, are you lying?
hold on. Let's say it's not hidden, okay? Let's assume that theory. They're
Not
not
a
hiding
theory.
it. Okay,
If you go
let's
to the
assume.
ocean, it looks flat, right?
I'm not sure about it. Like
You're not sure if the ocean looks flat?
it looks flat, but I'm
Yeah,
not sure
Okay.
it
well,
is
that's
flat.
fine. Okay, so that's the point. It looks flat. So if the ocean looks flat, they're not hiding it.
Well, it looked like we can't base like reality on how
On the way it
something
looks?
looks at first glance. Like we have testing
Why
and a
not?
lot of like. Well, because there's a lot of things that we don't look at. Like
Jedi, you got to take over because I got a bolt or somebody else
like
does.
I guess our sight is not like
Yeah, I'm around.
is not really something that we can use to derive like facts or science.
Really?
Not to its
That's funny.
fullest. Yeah, but I was just
So do they do astronomy in Braille? So how do they do astronomy? Do they look at the stuff?
No, they obviously look at the stuff, but I'm trying
Yeah,
to say
so we can't trust our eyes, right?
looking at something is not like a definitive proof of something.
I never said it was. The point is it's not hidden. It's impossible to hide.
Okay, but let's not touch that. Let's go back to the other topic about they. Who are they?
I don't know.
Because okay, let's say
Like,
they.
for example,
okay, you said,
my friend, is it your teacher?
Okay, but
No, please answer the question I've asked you. When you say they, is it your teacher?
I don't think so.
No, even if they, this is what Injo said earlier, even if they believe something, they're just repeating what they believe. They're not necessarily deceiving you with the intent to deceive you, are they?
Sure, I mean, so I'm gonna say, I'm just gonna repeat what you said. You said that they are not hiding it. It's just like an alternate story, right?
Hi guys,
Mhm.
how are you?
Okay, so who are they? Who are the people
We
telling this?
don't
Who's the
know.
people? You don't know.
We don't know. It looks
No.
like a historical kind of argument if you want to look back in history as to, when or how or who pushed the globe Earth and where that came from. Seems to be a theological background. It's a religious idea. But this goes back way into history, dude.
Why did you say theological?
Because it comes from places like the Catholic Church.
The round Earth
Yeah,
isn't like the opposite.
kind of. If you want to talk about the antagonism between science and religion, but we
But I'm
have to
just saying, like,
understand.
Antagonism.
from
There
what I
was no.
understand, like,
I
the
know.
Bible.
Yeah, thanks,
Hold
Enzo.
on,
There was no
Tommy. All
antagonism.
that.
Okay.
Hold on a second, Tommy. I just want to tell you, all that shit you heard about church versus science is a lie. It's a straight lie. I'm not even going to call it a deception. It's a lie. Okay, so if you look at Copernicus, who came up with the heliocentric model, the revolutions of the heavenly bodies, it was dedicated to the Pope, and it starts off to the Pope. It made it past the papal censor. Its forward are written by Catholic cardinals. Okay, Galileo, he wasn't prosecuted for he was prosecuted not for coming up with any type of heliocentric model. His actual prosecution, if you look at the trials, which are in the Vatican archives, was for forgery. He forged what's called an imprimatur, which is permission to print a certain book. You couldn't back then. You couldn't just have books printed, so you needed permission from the church to print a book. He forged one and gave it to the printer and had a book different than the one he said he was going to printed. That's what he was on trial for. Had nothing to do with the heliocentric model because the Catholic Church had already endorsed it.
Okay.
That whole story of science, I mean, Newton was like a crazy religious nut. A crazy religious
You're
nut,
saying
dude.
the Catholic Church had already enforced the heliocentric model.
They endorsed it, meaning they approved of it.
Yeah, I understand what it means, but I'm saying, like, yeah, I get that part. They did not reject it outright. Sure.
They wanted a model to help them predict
Maybe they
when
were like,
Easter was going to be.
sure.
You asked who they were. We're pointing out that, with all intents and purposes, again, this seems to be theological, where we have to go back into history to the inception of these ideas. And we can go back further. We can start talking about the Greeks and their idea of perfect plutonic solids. And if God was perfect, he would create the perfect shape. And from their idea, that perfect shape was a sphere. So they saw lots of spheres in the sky, so presumed that the Earth was also a sphere, and this was their theological understanding. So it appears to be theological.
You can also bring it closer to history and just look at the motion picture industry. And I mean, if you look into the history of like motion pictures, which is directly, basically the bedrock of modern science, is the ability to take high-speed imagery, infrared imagery, ultraviolet imagery. You'll find that there's been a very large conspiracy to cover up the means of trick imagery in the past. I mean, what our parents were shown in the 1990s about when timelines and certain technologies came into existence is just patently false. And when I say patently false, I mean that literally. You can just go look at the patents online and see, like, hey, infrared traveling mats were first invented, or at least first patented, in like 1931. The blue screen process was patented in 20. So, I mean, there's a lot of history that's been totally just muddled about what's actually going on. And it seems to be a theological thing, like 100%, where these people desire a very particular worldview, and, like, based on like the Copernican principle, right? And they'll do anything to sweep any evidence that goes against it under the carpet. And that's like an international conspiracy, right? Because, like, that's not just like the United States saying, oh, blue screen wasn't in existence or whatever. That's like the Russians not coming out and calling out the Americans. That's the North Koreans not calling out the Americans. That's literally any country you can point at, and they'll be like, oh, look, the Americans their timeline is right. We're all on board with that. Same with like 9/11. Not a single one of our enemies seems to even entertain the idea of saying it was fake. even though it would be great propaganda to disseminate towards the American public to cause mass distrust. None of our enemies are doing that. Enemies in finger quotes. Who are they? Well, they are leading the world. That's who they are.
What's up, Lanolin? Good to see you, man.
Just popped in for the morning. I'm not here for a long time because I gotta take care of some stuff outside the computer. But I'm doing all right. Thank you for
Awesome.
watching me.
Turning blue yet, DJ?
It's negative 18 at the moment, which is probably not too cold by Lanolin's standards. He's in Alaska, so. But yeah, it's pretty damn cold. Usually it's not too cold in the house, but tonight I can feel it. So it's going to be, I think it's going to get down to negative 25 or something tonight. Celsius.
Swings. That's cold. That's very cold.
Yeah, pretty cold.
So, who was the guy or person who asked a question about that? Are you still here? I can't remember your name, sir.
About what?
Yeah. You asked who they were. Do you understand the answers that have been given to you?
Yes, I do understand the
You got any
argument.
questions?
Yeah, I mean, there are a lot of questions, I guess.
Yes.
I mean, I can point to one specific guy. If you like want one specific guy, I can point you to a guy named Craig Barron, and it's like that guy, he knows he's lying to the American public en masse about the history of cinema. There's no way he doesn't know. I mean, literally, because he's talking about industrial journals and how he's read into them, and the history just shows it. It's like, dude, if you finger through any of these journals with any amount of insight in that industry, which he owns his own company called Matt World. I mean, he worked on The Empire Strikes Back episode 2, and it's like, just to know any of that technology, when you look through these industrial journals, it's like you can't miss it. Like, it's impossible to miss, and I mean it. Like, if you know anything about the field and how this tech works, it's like, oh shoot, yeah, you're just spewing lies, man. Why would he do that? I don't know, but I mean, you can point to some specific people. It's like, yep, they definitely know they're just spewing BS to spew BS. It's not even debatable.
Yeah, I got to say, while we have Lanolin here, I'm super impressed by his side view pictures. Super impressed. We need more of those. Everybody should try to get those kind of pics, even though I understand it's expensive.
Hey, I just want to tell everybody, you don't have to go out to a crazy frozen lake to do what we did. You just have to, all that's really necessary is to go to the lake, any lake particularly, and have your instruments, and just recognize that when you're doing them, it's important to know that one side of the lake is going to be different from the other side. So it depends on which direction you're shooting. Because so when we, in our observations, it was very consistent. If we're shooting from station C, I mean, it wasn't every day, because there were days where there were inversions, like where the surface was significantly colder than the air, and that would cause light to bend down. But it was very consistent where we were shooting towards the warmer half of the lake, and that means the density gradient is lofted higher. And I mean, it's super simple to know that if it's a warmer area downrange, and you're shooting from a colder area, that the light on a globe would necessarily have to bend down into the ground, because it's gonna, their whole point is it's so based on temperature. It has nothing to do with humidity. We can just ignore humidity in the globe model. That's what they like to say. So if it's based on temperature alone, your light is never going to make it an extreme distance if it's shooting into a warmer area, because it's going to end up colliding with the ground every time. There is no like hug the curve mechanism that will stop it from actually finally reaching floor. If you're shooting into a cooler area, of course, that would the whole idea would be that it's going to rise up, it's going to bend up, even in a globe model. So you basically just have to go to a lake get your weather stations set up, they don't even have to be extremely accurate, because when you're accounting for humidity and the release over lakes or over ice lakes, there's so much humidity leaving the ground that like, if you can collect your wet term and your dry term, which if you can do some simple searches on Google or DuckDuckGo or whatever to try to help you sort out how to do that. I'm sure you might even be able to use AI to help you run calculations. A lot of them are really good at math. It's not really all that hard. It's like not out of the reach of people to do these anymore, and you don't have to you know, get in danger. So, and then you can verify it. If you have a theodolite, right, you'll be able to calculate like how much drop there is in the theodolite during upward refraction, and then you'll be able to see if, during downward refraction, you'll be able to verify in the sites of your theodolite, oh, look, at the surface, it's above my theodolite crosshair this day. Then on another day, you can see too far, and it's like, well, it's below my theodolite crosshair on this day. So it's just, we got to be accounting for surface temperature. We got to be accounting for, the air characteristics. That's what the globe model doesn't do. So.
Oh yeah, that's what I'm always requesting from them. And they're making hyper-specific claims as well. They'll be saying, "Oh, this thing off in the distance, 3 miles away is, it's ever so slightly lower than it should be. Therefore, that matches up with a globe." It's like, okay, well, have you taken all of the potential variables into consideration? They're like, "Oh yeah, we put it into a computer model, and that let us know what the refraction coefficient was." It's like, what? So you just reverse engineering it onto a globe model, or they'll just use standard refraction, and which is basically just guessing. So yeah.
100%, man. I mean, I think it's pretty interesting. If you see the movie, you'll see where we pointed out where in the in climatology maps where they have to bend the contours to the maps, which means you have to be accounting for the surface boundary being like a curved surface if there was one, right? So instead of using genuine measurements, instead they imposed a fictitious value, and specifically it was a fictitious value of the relative humidity. So they didn't like impose a temperature value. No. They imposed a fake humidity value, and it's because of how much of an impact humidity has on the final outcome. Right? Okay, I know. Sorry, no, go ahead and do your stuff. So I'd like to point. I want to just take the moment, since I seem to have the soapbox to stand on for a second here. The biggest argument that has been posed for, I think, every year that I have ever been in any one of these lobbies, right, where people are trying to say, well, you need to measure this or you need to measure that, and you need to get like your these hyper-specific high-resolution measurements. Otherwise, it's all, just nonsense, right? One of their biggest claims is that humidity is not important. You don't even have to account for it because it has such a small change in the refractive index. And that would be true, right? What their claim is that it doesn't change the refractive index very much, but that's only true if the humidity is stationary and not moving, meaning like it's all the same temperature of the surrounding air. And I should get some headphones here or something. That's so. It's all the same temperature of the surrounding air. They're not going up or down. They're not carrying the temperature up or down. And that's what I have been told. Not the part about them not moving up or down, but that it has such a low impact on the environment, on the refractive index. as like just a bold-faced lie. I mean, in so much that like when they're taking into account the environment, they literally use fake values because they have to use fake values. Not because they want to use fake values, they have to use fake values. And yeah, if you start trying to do like real ray tracing, like density, it's really density tracing. It's not really ray tracing. You're like measuring the density gradient, and that helps you calculate the ray and where it will go. If you start really trying to do that, and you want to hit targets that are really far away, you're going to have to start taking into account the real world. And when you start doing that, the mathematics becomes a flat Earth. Like they start using flat Earth mathematics for it. So it's pretty disgusting, honestly. To me, it shows a gross misunderstanding from the people in here trying to tell us how much they know about optics, but all of their assumptions about how humidity impacts the refractive index is all based upon it being stationary and unmoving, and without accounting for the release rate at the surface, and without taking into account the surface temperature, and the fact that because there's 62%, or at least we're told that there's 62% the molecular weight of air molecules of the standard weight, so they rise. Even when the surface is colder, they often rise. Unless there's immense disparity in the surface temperature, they can also condensate, but that's like a multi-day cycle, you know, like not a multi-day cycle, a multi-event during the day cycle. So,
right. And so a lot of the mainstream literature seems to say that the humidity like lowers the refractive index because the water vapor or whatever is less dense than the gas molecules.
right, you have density dilution right at the surface, so you have higher pressure because you have, so this is like the idea of having like if you have ping pong balls, right? And let's say they're solid core ping pong balls. Like let's not take it, like think about the density of the ping pong ball, just size, volume, okay? You have like the volume of a ping pong ball, and then you have sand, okay? And if you have sand being injected from the bottom, it'll fill in all the gaps between the ping pong balls, right? Now, this is just a volume thought experiment. It has nothing to do with the density of sand or the density of the ping pong balls. The whole idea is that you're filling in all the gaps with humidity, because there's a capacity, you know, like humidity and air. When you add humidity to the air, it's actually filling the capacity. But what it's doing is it's diluting the total density of that air. Okay, so as you fill it, it dilutes it down. The pressure increases, but you're actually dropping overall density. A lot of it has to do with the thrust, because it's picking up those ping pong balls, like literally, like as it comes in from the bottom. It's like dumping a perfume on the ground. The perfume rises up. It displaces the air. It doesn't just mix. It literally will lift the air up because it has a positive thrust. I mean, if you go outside on a super humid day, you can actually smell the humidity in the air, you know, like a sweet smelling perfume, except it's not so sweet, but it's the same thing. And that lifts up your density. So it's a large part of it. The temperature change, that's also a large part of it, because if you have especially a warmer surface, and the vapors are being released from the surface, let's say it's 12 degrees warmer at the surface than it is in the air, those vapors are 12 degrees warmer when they left the surface, and they don't discharge all their heat all at once. So you actually have warmer vapors in the air, and so you have air that's warmer per molecular weight near the surface. Like the difference between 10 feet and 0 feet in terms of overall pressure and overall density is a very small difference between 0 and 10 feet. But
Yeah, exactly. Yeah.
So the whole premise of these measurements is that it's such a small change that this buoyant force, and it's a measurable force, and that's why historically they measure it as a force, because it is a force, like measurably, and it's historically been done through vent dynamics, the whole idea of pressure vent dynamics, where there is an off-gas effect happening, and it's putting something which is more buoyant underneath something which is heavier. And the Archimedes principle is a very well-known established part of science, where it's going to create an upward thrust, and that thrust is being enacted upon the thing that's above it. So and that isn't just a liquid principle, that's also a gas mechanics principle. So yeah, it's...
So what you're saying is it's going to be pretty rough for the globers to get a very specific globe measurement.
Right. Well, someone said earlier that they went with a theodolite, they measured it, and they said, oh, look, it's a little bit lower than it's supposed to be. It's like, for that to even happen on the globe, it means on that day, if it was a little bit lower than it was supposed to be, that's not a globe prediction. That's like a, what the heck is going on? Because in their model, for light to even move in a semi-straight line is borderline. I mean, it's like, we're talking about an impossibility, which is like unfathomable. I mean, it's a massive, unlikely scenario. And when I say unlikely, that's an understatement of the century. It's like immensely implausible to ever happen that light would ever travel in a truly straight line on a globe. In fact, it should almost always look like you should see further on a globe, just because light would be bending down in their model all the time based on the accepted environment that they choose to accept, which is a false environment. Realistically, on a globe with the true environment that we can measure and do measure, not just can, but we do measure, light bending up would be very common, and you would almost never be able to see to the true like if there was a geometric horizon, you would almost never be able to see to it during the day, especially over land, and quite often over water. You would like never even be able to see nearly as far as you would hope to see if it was all traveling in straight lines. Not even close. So
Lanolin, can I ask you a follow-up question on that? Sorry, DJ. It's just it's pertinent.
Yeah, go ahead, man.
We have a gentleman who's come in here, I think, at least 4 times in the last maybe 3 weeks, who has argued for the globe based on I forget the official name for it, but it's this giant survey that was done in India, I don't know, a couple hundred years ago or whatever, whereby they've taken sections, right? They surveyed different sections, different triangles, in triangles, I should say, of various sizes, using a theodolite or whatever it's called there. I think they have different terms.
And they're assuming straight lines.
And sorry?
They're going to be assuming straight lines.
Right. Now, anyway, so the claim is based off of those measurements. When they do a series of angle measurements and then kind of add them all up, forming triangles or whatever, and they get an angle, an internal angle sum of something greater than 180 degrees.
Right, a curved triangle.
They attribute that excess to a mixture of both refractive effects, having bent the light, but they also include in that excess, or they allege a component of that excess being due to the curvature. And I've asked this guy incessantly, how is it that they can actually quantify the proportion of that excess being because of the light bending or because the ground is curving? Like, how do you determine how much is because of which one? You know what I mean? And what the guy had done basically is, say that you go to a position, you go point A, and you're taking an angle measurement to point B. Well, you do that over, multiple times over the day, or multiple days, right, in different seasons or whatever, and
So he's saying we used an average. Yeah.
And you average out, right?
Right.
But even if you do that, you're still like that
Right.
average is still has both these components in it, right? So it doesn't answer the question. You know what I mean?
No, it
so like,
doesn't.
how do they justify this kind of like seemingly sloppy, method full of assumptions, basically?
Because they're assuming that the average refraction during the day is downward, and so the whole idea is we're on a downward refraction. And I mean this, in all instances, they're trying to say the average is going to be closest to what reality is. But during the day, especially in a place like India, where there's, truth be told, it's probably more based on temperature in India than it is on humidity. I just assume because it's so dry. But that doesn't mean there isn't humidic effects. It's just there is going to be a lot more temperature internal fluctuation, and humidity has less of a multiplying effect in terms of the smoothing of it. So you can get a lot more variance in your observations because heat's a little bit more finicky, but it still should be very consistent. I would say it just, there is more potential, I would say, in terms of extreme upward refraction. But I mean, you can just see that in the desert. If you look in the desert, you can see some really serious extreme upward refraction. It's just because the sand holds heat so frickin' well compared to the air, right? So the inversion is much higher. So what I'm saying they did, because I'm just 100% certain if that's what they did, if they averaged it, it's that they're getting the average of upward refraction through the day. So it doesn't matter how many times you go out there. What average upward refraction will cause your horizon to be closer than it really would be, right? It actually brings your horizon in, especially on a globe. Okay, so if you're on a flat plane and you have upward refraction, it doesn't matter how many freaking days you go out there, especially during days, right? Because days, it's going to be where the ground is usually going to be warmer than the air, like predictably so. And that's going to cause upward refraction across all your days. You'll actually have a shorter horizon. So if you have a flat plane and you're trying to average just during the daytime, the distance to your horizon, and somehow apply that to like physical geometry, there is no way to separate it. You would have to be taking surface temperature measurements, like we did on Tustamina, and air temperature measurements, and your humidity, and your barometric pressure. And you would have to do the calculations for every single one of your observations, not just in one direction, in both directions. That's what's really important, is if you're shooting from one theodolite back towards the other theodolite, and you're making these triangles where you're looking back at each other, like refraction isn't a one-way mechanism. It's actually like if I'm looking at strictly upward refraction from one point of view, from one side of a lake, the other guy can be seeing what appears to be downward refraction. Because, for example,
wouldn't that assume the gradient is in one direction or another as opposed to up to down?
Well,
like a horizontal gradient versus a vertical gradient.
The idea is the vertical gradient changes. Okay, so like and I think of it more of like a diagonal. When I tell people the gradient, it's like you're actually like just changing on a diagonal, because the diagonals kind of assume that there is a horizontal change and a vertical change, and that's how I like to think about it. And it's because it depends on how far you are to the target. Think of it like ocean waves, okay, ripples, like in the on the surface, right? If you put different layers of different density water, right, in a tube or in a bathtub, right, they'll separate, and then you disturb it, and the waves, if they're different densities, right, you'll be able to see the surface of each layer. Okay, and where that surface is going to be the densest layer, because you have all the weight above it pushing down, but then you also have the thrust from the third element, the vapor, but also the surface temperature, which is also technically another element that you have to account for, excluding vapor, in your measurement. So if they're not doing that, then they're not doing anything. They're just using averages, and on average, light bends up very consistently. Like it's a very consistent thing you can predict. Like if you're especially over the ground, like over dry ground, it's like if it's daytime, the ground is probably warmer, especially if it's sunny, is almost always going to be warmer than the air. So you're going to have a lot of heat release from the ground, causing a lofted density gradient because the heat is warming that air above it. That's a thrust. That's a literal thrust, where that warmth is trying to raise up a buoyant force, and it's lifting the cooler air up. And so there's a pinching effect above the surface where that warm air is pushing up colder air, and then the colder air above it's trying to push down, and it's how much that is offset. That tells you where the top of your wave is. And where the top of your wave is in gas mechanics, when you have a surface like this, a surface boundary that has a temperature release, then that's where your densest point is.
So through all that you said, is there a condition above the medium? You're looking across the median of the Earth. Is there a condition where this effect can cause a curving ball to look flat? Is that what refraction do? At what?
Yeah.
Specific?
So like I was saying, there is like if there was downward refraction consistently on a globe, right? If it was a consistent measurable environment, yeah, it would make things look pretty darn flat. Yeah, that would be a mechanism. The problem is you need the mechanism for it. That is the problem that the globe has always struggled. And when I say struggled, it's not just struggled. I mean, it has always failed to procure. It doesn't have a mechanism to actually cause as much downward refraction as would be necessary. I have from my own survey on Testamina, some examples of downward refraction where you can see it, and it's on a plane. Downward refraction can let you see sometimes a little bit further, but it has to be very, very light. If it's not even really seeing further, it lets you see over things, I suppose is the right way to say it. But any refraction is like destructive per se. So like downward refraction is fairly destructive. Actually, it's incredibly destructive, but so is upward refraction. If you look at examples of upward refraction, it can make it really hard to see things off in the distance really fast. And downward refraction does the same thing. I have an observation where I only wrote out, the camera was at 3.5 feet above the surface. I'm on a snow machine and I'm riding away from the camera, and I only make it about 1.9 miles from the camera and I disappear. And there's upward refraction. I mean, not upward, downward refraction going on because we have snow machine tracks off in the distance, which are beyond my position, and they are like up at the height of my head. So we're seeing the ground on distance look like a bowl, where it's like there's the snow machine tracks that are on the surface of the lake and they're at the same height as my head. And I'm just a little bit closer. And then I end up getting squashed like an Oompa Loompa, right? Like a Mario, whatever they call those things that you jump on as Mario, squishes down, and you can see my snow machine tracks all the way to the point until I disappear.
But what about a laser? What about a laser? Because you're talking about light that's reflecting off a surface.
Yeah, so a laser. So if you put a laser on the other side of that, it's going to cave down. So it's similarly, right?
Why would it?
Well, because it's coming from an area that's warmer. Like I was saying, I was consistently writing toward. Listen, no, let me answer. Let me answer.
All right, go on.
Let me answer. We were consistently aiming towards a warmer environment with the camera, with the P1000 on our observations. So any light going towards the warmer area, right, should on a globe be bent down into the ground. Anything coming towards us from the warmer area, likewise, should also bend down towards the ground as well, even faster, because it's going from warm air to cool air, and the cooler being the surface. So
that's not the only thing that's going to dictate the light's path, though.
No, you're right. No, that's what we've been saying. That's what we've been saying. So when we're talking about downward refraction, the reason why you can see my snow machine tracks all the way up to 1.9 miles is because they're being the light that's coming off of them. Like if you were like
looking at it straight from the side, right? That's a very shallow angle to be seeing. So it's actually light that's being projected up from the surface that's then being bent back down to where it looks like I'm looking at it as though I'm closer and above it. Okay. So a laser, it's going in a very horizontal direction if you're pointing horizontal, right? And you'll see the equivalent of whatever angle it left its position from. So it's kind of like these things on distance spread out in a cone. I mean, a laser spreads out in a cone too, but you're trying to restrict how much of a cone it's spreading out in. And again, I'm with you. You actually do have to account for other factors, not just the angle at which it leaves, but you also have to account for the humidity, the surface temperature, barometric pressure, the whole thing. They're all intercorrelated. So, like we have an example where we can prove, look, there's downward refraction, and it made it almost impossible. In fact, it was probably the shortest distance we ever recorded from the camera. I don't think there is a single observation where we could see less far than on that day of downward refraction. I'm pretty sure we could almost always see on upward refractive days almost 3 miles. I don't think there's a single day that we didn't actually make it 3 miles from the camera when there was extreme upward refraction. But on downward refraction days where like the surface actually is appearing above my head, I was only able, like I said, on that day particularly 1.9 miles. So I think downward refraction is significantly more destructive because it ruins your ability to see things at the ground level, especially. Like it creates a skip zone, a dead zone, kind of like in
So refraction
radio.
is also a phenomena that causes balls to never look like balls, because you never see a ball, but you're saying refraction can cause you not to see the ball. So you never see the ball because of
Only if
refraction.
only if the environment was suited the way that they claim that it is, but it's not. That's the thing. That's why I brought up that in the literature and through history, they have to claim the environment is different than what it is. It would work if we had a like you would be able to see 30% of the time, not 30% of the time, on average, 30% further is what I meant to say. So you would be able to see, and this is what they claim, that on average, you can see 30% further than you should if it was light traveling in straight lines on a globe. That would work if the environment was suited that way, meaning if humidity was hydrostatic, meaning it wasn't moving up, it wasn't moving down, it was homogenized like milk. Like it was perfectly blended and it wasn't changing elevation, it wasn't carrying heat up or down, then you could have a globe where you can see too far consistently. And that's what they do in almost every single refraction model. If you go to like Walter Bisland's calculator, his Earth curve calculator, basically if you pay really close attention to when you're moving his refraction slider in the globe model, you might recognize that all it seems to do is change how curved the ball appears to look in his model, right? It just seems to it just makes the globe look way bigger than it really is. It's basically just changing the size of the ball underneath you in that viewing program, right? And that's done particularly that way because it's pretty deceptive as to what's going on. That is the equivalent of just putting a millimeter thick lens in front of your eyes and saying all the refraction is happening 1 millimeter in front of your eyes. His model does not show any compounding refraction, meaning the light ray is just assuming to be going in whatever arc is perfectly necessary to match the size of that said globe. Okay, because that basically light in that model has to travel in incredibly beautifully curved arcs that are not they don't really compound all that much. That's the problem.
Yeah, so
So
Lanolin, is it fair to say he didn't offer any ray tracing model, so therefore no environmental effects were actually modeled? It's more of
right.
just a spreadsheet calculation. Got it.
Yes, that's exactly what he did. He offered literally no true ray tracing or density, and I call it density gradient tracing. But yeah, he didn't do any of that. There is no wave that he's showing over the surface. It's just at whatever distance you're saying your target is at. He's in his model. calculator. He's just assuming that the air is perfectly homogeneous, meaning it's basically a perfectly machined glass lens that you'd build in a factory, to where you can always get the perfect trajectory, the entire arc of that spherical surface. So then you'll be able to see your target. It doesn't account for surface temperature. It doesn't account for any of that. It just assumes the air is in free space with a surface with no effects from the surface.
And one thing on that, what, if I may, or sorry, Yoder, go ahead if you had a follow-up.
Yeah, I was gonna mention real quick. It would be necessary then for every arc of light to have a different grade of bend in order for the entire rounded surface to be lifted flat, because you'd have a different arc at one grade that's close to your eye, to your observer point, bending at one rate, and then you'd have another rate for what's much further down or around the far side of the curve on the surface.
Right. Yeah, you just hit the nail on the head.
Right. That sounds like a conspiracy theory.
Oh, it is. It is a conspiracy. It's absolutely nuts. Because again, if you're dealing with a surface which is, like, let's say, colder than the air, there's no mechanism for them to go at different rates that are perfectly consistent at each layer. It's like, no, it's going to get dragged down towards what's supposed to be the colder air near the surface, right? And it's inevitably going to hit the surface. So, like, on our night on Testamina, we shot 18 miles from Station A to Station C, again, shooting from a colder area into a warmer area where the surface is becoming colder than the air, like, at a point. Like, it really is. I mean, it actually ended up balancing out. It was 32 degrees in the air, 32 degrees on the water. So, I mean, it had almost perfectly balanced the temperature as to the surface and to the air. But the light started at a certain density gradient, meaning if we're shooting into that area that's warming up, again, the density is simply going to get closer and closer and closer to the ground, because that's how where the density, if density was always close to the surface, like they're claiming, like it's always right at the surface, it just means it's, again, going to get dragged down literally to the surface. And we could see it. In fact, I have a shot where it's literally going above my head and hitting the trees above my head, and it's like it would have never made it to my head, would have never made it to our location unless we were aiming quite a bit up. I mean, like quite a bit up, to where we were basically going through several layers, which with the green laser we did. We had, we were free aiming that one, and I'm shooting back towards him, and it was being bent up so much as it left my position that it was able to change its angular direction, right? It's basically the degree at which it's leaving the surface, its slope had changed, and it had to pierce through several other layers, okay, before it was forcibly dragged back down. And that's why we got a 7-image Fata Morgana, was because it left the initial layer, okay, it intersected with the wave, which was coming closer to the surface, mind you. Like, it was actually, the density gradient was getting closer to the surface as you go towards Station A. And our laser had been bent up so much that it passed through that layer, went through 7 other layers, and bent back down, and then followed the first layer, the densest layer. And it's amazing to see that. I mean, a 7-tier Mirage, man, I've never seen. I didn't even know it went that high, Nobody talks about 7-tier Mirages. I think the highest I've seen written in literature is a 5-image Mirage. That was pretty cool. Okay, I'm trying really hard, DJ, to get you that raw picture. I just keep getting distracted. So.
Oh, yeah, no problem. No rush either. Awesome. Yeah, I posted some pictures of the Fata Morgana laser in the side chat. I've never seen anything like that either. It's pretty crazy.
And that's not even that one's not even of the 7. That one's 1, 2, 3, 4. That's a 5 right there that we got.
So what are we looking at there? Like, are we looking at an actual change in direction of light, or just an apparent one where the conditions have made the laser appear to be where it's not, but it's actually just traveling in a straight line?
Right. So in the globe model, for that to happen, there has to be more refraction, meaning more change in angular direction. There's no there like you got to keep in mind, even if you're just looking through a lens, right? What you asked would basically be saying, am I wearing a set of sunglasses that have a lensing effect right in front of my eyes that just cause the light to look warped, but in reality, it actually was going in a straight line. It's just the sunglasses right in front of my face causing the problem. And that's what I'm saying. It's like, nope, negative. Light is traveling through that sunglass, which is actually spread across the entire distance, and it is angularly changing its direction. And what we're seeing is we're seeing the side of it, right, as it goes through those
Hello,
layers.
Earth is a cube. Hey bro, Earth is a cube.
Just hold up, man.
So what I was trying to say was we are seeing a displaced position than where it truly is because we're looking up through these layers, but we are seeing its interaction with each one of these layers. So you wouldn't be able to just point at any point in that refraction and be like, that's exactly where the laser is. No, that's just the total sum of refractions to our eyes reaching us, showing us that, hey, look at how warped that image is. I mean, it is warped. It is definitely being changed. It's definitely being bent. But yeah, you wouldn't be able to, like, shoot a bullet at that light and actually have it intersect the light probably at pretty much any point you're looking at right there. It wouldn't be where you're aiming. So, sorry, go.
Right now, I guess it was a kind of stupid question because, like, yeah, it has to, like, if a light is passing,
it's not
really, it's something that's changing, like, it's capable of changing its direction, and it reaches an observer's eyes. I mean, the light has literally changed direction.
Right. That is the biggest qualm I have with Walter Bislin's whole presentation of how accurate his entire model is he's just lying to people. To be able to code what he did and to be able to to be able to do even what he did on his website means you recognize there's a lot of different variables involved, and he's ignoring the most important, which is the bending at any given point. Like, you actually have to have 2 points of data to be able to make a model like he's trying to show on his you have to have 2 localities. You can't just have one. I mean, you can, but it's only going to work in one direction. Like, you'll only be able to make small short distance predictions, maybe like 3 miles, and that's if you're in a very unchanging locality, like at a lake. Like, you would be able to do it like at a lake only because a lake has a very consistent locality design. The water is consistently a similar temperature throughout the entire lake, unless, a warm spring is entering the lake at some place, but that's usually a small area. If it's just a closed body lake, it's a pretty consistent locality. You could make some predictions from just one locality, but to be able to, like, compute like what's going on with this fata, you'd have to do what we did. You'd have to have 2 points. I mean, it's just, otherwise you're just spitballing in the dark. I mean, you can model in the sense of, you can just kind of guess and be like, well, I believe in this model and therefore this is what must be happening. And that's what they did with the Rainy Lake observations, is they just said, we're just going to assume that it's this model, and we'll put all of our measurements in a computer model and say we measured it. And they didn't. So they didn't really measure it.
They did the same thing with the so-called black swan, right? The oil rigs. I think there was an article posted on his website where he used his calculator to kind of, like, justify their interpretation of that observation being, just on a globe, but with mega refraction, and the kind of modeling of what would be, the proper phenomena or the actual phenomena to render or to yield that sort of observation. He puts at the top, right, some diagram, temperature related diagram about it. But he, as you said, he omits the rest, right? He doesn't account for the humidity or the air pressure or whatnot, just temperature. And if you look at that graph that he posts, it's obviously kind of imputed, just inferred, but it's an absurd claim because the graph depicts the necessity of something about over at a certain point in the trajectory or the entire trajectory that there would have been, I guess, an on average temperature change of between 10 and 15 degrees Fahrenheit or Celsius throughout like a 10 meter or a 15 meter altitude difference or something like that.
Yeah. So, and by the way, you said he accounted for the temperature. I can tell you right now, he only partially accounted for the temperature because they assume in these models there is one temperature lapse rate and there is two temperature lapse rates, and that's why you have to account for humidity, is because humidity has its own temperature and its own lapse rate as it leaves the surface. Even if the surface is colder, it has a cooling effect. If it's warmer, it's got a warming effect. So
sure. I guess what I meant by like accounting for temperature is, I mean, all he's doing is showing one variable out of the multitude of necessary variables, just temperature. Now, whether he's doing it one way or both ways or what, that's a secondary issue. So
he's using one half, and he's even using one half of it, is what I'm trying to say.
Oh,
he's saying, I'm just going to use one
even
variable. Yeah.
It gets even worse than that. And just a second, Lanolin will find this kind of funny as well, because what he did, he had like a preset on the Walter Bislin calculator where you can put in the black swan observation, and it's like, okay, if he manipulates the temperature gradients, if refractive index gradients a certain way, it's like, okay, now it works on a globe. But what he had to do, which we worked out later on, was he put in a layer of fog that made the fog, like, that hid the background water. Okay, and when we did the same thing and removed the fog, this is what was in the background. And we added some surface to it just as a joke. But he actually had to add some fog because obviously you never see a scene that looks anything like this. So for him to make it work on his ray tracing, reverse engineering model, he had to have it set up so it had this giant, what looks like a tidal wave in the background, and he dishonestly removed it by using fog.
Oh, forgot about the tidal wave. That was hilarious. Yeah, big wall of water like 80 feet high.
Yeah. This is a screenshot from his simulator or whatever you want to call it.
Yeah, it really is no joke. To see the distance that they're claiming we can see on a globe would make the globe look like a bowl. Straight up. Like, you wouldn't be saying it's going over any curvature ever. And it's just absurd because downward refraction is very destructive, because like what was mentioned earlier, somebody pointed out how it sounds like a conspiracy theory that at all the differing heights, the light has to move in an arc at a different rate, in a nice perfectly curving rate at each height. And it's like that's the only way to get that tidal wave wall to look like that. And it's insane.
You're saying it's much more dynamic and unpredictable? Chaotic.
Yeah, it is so much more chaotic on a globe. Nobody, like, we quite literally would never have grown up thinking there was a physical curve that you could see. No one would have ever thought that, because we would see things day to day that are just so absurd all the time that we never see. That's what I'm saying. It would just be just blatantly in our face that we're not watching boats going over a curve. We're watching them get crushed by the optical phenomena that the globe would be causing. So, yeah.
So, what your side views, man? How's the laser visible from you?
So yeah, what we did was, I have a 4-watt dual diode laser. So it's actually two diodes that are 2 watts, and they're joined in through a beam splitter, and well, I guess you would call them in this case a combiner, but that's what it's doing. Is it's they're being combined, and it's going out through the front as a single beam, and so it's a pretty powerful green laser. It can blind you very, very easily. It's got a half angle milliradian of like point divergence of like point. It's either 0.123. It's like 123. It's like something like that, or it's like I can't remember. I can't remember what decimal point it is. I think it's 0.12. I'd have to go type in my stuff again. And I don't have it written down next to me, but it's basically at 6 miles, it will have diverged like 4 feet, I think. So it's pretty accurate. It's not like military grade, but it's pretty darn accurate. And
because usually, like you see on on your YouTube videos, and they're showing a laser, they have to like spray some aerosol there or something so that you can see it. Like, and I was just wondering, like, well, that must be some
in this instance
laser use.
Yeah, we used a pretty strong laser, and we also waited. We waited for a day where the vapor discharge from the ground was pretty high. So like in our side view laser, you can actually see the humidity dispersion zone, which is where when the humidity is under pressure, it's actually in a smaller form. It's actually a smaller water vapor because vapor changes size as it goes higher. That's how you end up with clouds, right? As the vapor actually begins to expand as it gets higher. When it's under more pressure, it's actually smaller. And so in our shot, you can actually see the lofted haze, and that's the area where the vapor actually starts to spread out, and there's so much of it that you can physically see it with your eyes. But it continues to rise, and we actually have pictures where you can see that the vapor actually continued to rise through the night. So we were waiting for that night. I mean, we ran out of food on that night. That was our last night there, and we were like, oh, amen, thank you, Jesus, that this happened, because we were concerned we wouldn't be able to see it from the side, because we did some test shots, and yeah, we could see it, but we also had the exposure on the camera. I had my camera, I specially selected my camera because I had an incredibly high light sensitivity. It's a 3-stacked CMOS chip. So I had bought that camera specifically because of its extreme light sensitivity. Like I said, the lens was we bought strictly because it was the lowest distortion lens we could get our hands on. They do make a wider one than the 12 millimeter, but it actually has a worse distortion rating. The 10 millimeter has a higher distortion rating than the 12, so we went with the 12. Golly, sorry, I'm trying to collect my thoughts. There's so much to pull out from the drawers of my mind.
I'm wondering what the length is there, like in those images. How much laser are we seeing?
About 12 miles from left to right.
In the side shot? In the side
Yeah,
views?
in the side shot, yeah, about 12 miles. Whoa. It's a little more than 12 miles, but yeah.
Wow. Like, is that from distance from the beam, or the beam distance itself that we're seeing? Like, how long is that laser?
The beam distance itself. So if you're actually trying to say how many miles of beam am I seeing, it's about 12 miles. It's a little more, but I don't want to throw out like a hyper specific number. Okay, but the distance from the camera to the center of the laser and the center of the frame is about 3.5 miles, and then on each side of the frame, it's roughly about 6 miles to each side of the frame. When I say roughly, I mean it's like incredibly close. It's almost exactly 6 miles. It's a little bit more than 6 miles, but it's really close. So, yeah. Yeah, no, it's a pretty cool shot. So,
hey, what's up, Lanolin? I was telling them in the side chat, they're saying like, hey, this is a lot of good information. I was like, dude, like, I'm saying you should see when you do your fake moon landing presentation. That is awesome, bro. Like when you go through all your filmography and like show all the the magic of, you know, film and movie magic. Like, I hope you can do that one day in here. Good to see you, by the way, in here.
Thanks, Apocryphon. Thanks, man.
Maybe one day you can go through that stuff with them. So you have a lot of good information on that.
Yeah, I definitely, I definitely could. I have to go to the funeral home with my wife today at 2:00.
Sorry to hear that.
It's in
Sorry to
a
hear.
few hours. It's okay. She's with Jesus now, so it's not my wife, but her mom. So.
Yeah, I know. Yeah, condolences. Well, next time, maybe next time, if you could come back and when you have time and go over your whole like presentation with them. I was telling them before, I was like, I was so disappointed like that in your documentary you didn't go deep into it. I was like, I was telling DJ, I'm like, bro, I was like, that's the only thing I wanted, you know, more of that film was like your whole fake moon landing presentation. So
sorry, it's just when you're going on 2 hours, it's like it's hard to get people to watch anything that's over 2 hours.
Yeah, maybe you got to do a part 2, you know, where you go deeper into the film stuff, exposing the moon landing.
Ultra extended cut.
Right. I mean, for those who are craving the info, they're going to watch it. You know what I mean? Like, especially because you have such a informative, a lot of information. Like people that do love information and knowledge, they're going to watch it. They're not, short attention spans. For those who really do look for the truth and do want, who do love knowledge, like I think they'll watch it.
I think you're 100% right. Just just got to get there. Get to that point.
All right, we've got Exo in the chat. Sounds keen and eager to prove that the Earth is a globe.
Ego.
What say you, Exo? You gonna mic up? Have a chat. Sounds like you've got the goods. You've got the proof that the Earth is indeed not what we observe and experience, that being flat and motionless, but rather a big spinning ball in outer space. Let's hear it. Come on, let's go.
Said he can't talk English. He can't speak English, but he could type it. It's probably a sock account. That's why they don't want to talk, because we'll recognize the voice.
Yeah. Is that you, Rob? Is that Rob Utah?
Probably a sock account. For sure.
It's not a fresh account, so got to give him the benefit of the doubt. Anyway, he doesn't want to mic up. He doesn't want to mic up. Can't make him.
Yeah. Hey, Lanolin, I'm glad you brought up that how his calculator, he doesn't account for like the conditions that are variable, because you know how some of these like globetards, they're like, flat earthers don't believe in refraction. You know how they make that false statement, but then it's kind of like projection, because they truly believe in perfect refraction, where it's always going to line up perfectly to where they need it to be. But if you look into the math of even what they're saying, how you can see the oil rigs, like 20 Cups was talking about earlier, one thing that he doesn't have in his calculator was refraction when you slide it. I wish he did. At least I haven't seen it. I wish he would put what the value is, because for the oil rigs to see 10 miles at 1 foot, that's requiring a negative 150 K value. And that's asinine in so many levels and ways. But for Globers just to blindly like believe, oh yeah, that's possible. That's totally normal. That you could have a K value, coefficient value, just be negative 150. That literally becomes like a concave. You know, you're now in concave world at that point. If you're trying to say, oh yeah, everything just went up, you know, at negative 150. So it's interesting that he doesn't have, like, when you slide the refraction ruler, it's interesting that he doesn't do the what that equates mathematically. Because I think if people can see it just going higher and higher and higher and higher, like they'll be like, whoa, like this is not even normal. That's not even reality. You know what I mean? Like that's not even no one can get that.
Again, his model presents it as though it's just the globe under your feet getting bigger and bigger or smaller and smaller. That's it. That's all he does. That's his whole model, is just change the size of the shape beneath you. And in that way you'll never see like his model. This is a guaranteed way to know that his model is wrong, is you can go out with a theodolite and you can go to a day with downward refraction, like genuine downward refraction, and something which should be hidden, okay, from an object. Like let's say you're looking like you have a 6-foot piece of plywood set up halfway downrange, and you're looking, like, let's say 3 miles, and your theodolite is at 6 feet, so you're looking just over the top of that piece of plywood, and then you have something that's only at 4 feet that should be hidden behind that plywood, and you'll be able to see it during a downward refraction day. Well, that means that the world in that instance is looking concave. Even on a globe, that would be a concave day. Well, guess what? None of his model, no matter how much you turn that refraction slider on his website, will you ever be able to see an object which should be hidden behind another object appear to be above it. It will only make his globe look more and more flat. It will never make it look like a bowl. I mean, it's just a straight lie. His whole model is just him knowingly deceiving as many people as he can with the appearance of authority of sophistication, which comes from sophistication.
Right. Yeah. Even if you were to have like yeah, and you're exactly right. Like in regards to all he's doing is just increasing the size, because when you increase the size, you then have a larger radius
with the appearance of authority. Sophistication, which comes from sophistication.
Is my thing messed up?
No, that's Ocean. I think Ocean was
You're exactly right. Like
hot micing.
Oh, he's like replaying the video or something. Okay, Ocean, you're hot micing. That was weird. I was gonna say that you're right. Like it just makes the Earth bigger, 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 and that's how you're able to see it, quote unquote. Because if you do the math, like in order to see 10 miles from 1 foot observer, you can do that even like at an 8 coefficient, a refraction value of 8, which is also super high. Like that's not even normal.
Absurd. It's absurd.
Yeah, but that will give it a 66,000 mile radius. So technically, you can see 10 miles from 1 foot observer on a ball that has a 60. This is all just math, obviously. On a ball to see the surface 10 miles from one foot observer height. Technically, mathematically, you can do it if the radius is 66,000 miles. Then, lo and behold, it'll be equivalent to you being, 6 feet tall, seeing 3 miles on a radius of 3959. So like it's all it's all relative, but no glober believes they're on a 66,000 mile radius. What did they do? They just yanked the shit out of the coefficient, a refraction coefficient, in a negative value. Again, concave. They just bent it up and then said, "Well, there you go. Mathematically, it works." It's like, wow, dude. These guys, they're so dishonest.
Yeah.
I love how their math destroys their math.
Their math destroys their math, but they will never present their math as destroying their own math. So, like, it does. I mean, I get it. It can be funny, but in the other way, it's kind of not funny. But
yeah, you're right. It's really asshole-ish, right?
It really is. Yeah.
Well, they just say, well, nothing's perfect.
None of them really know what they're talking about. Like even the anti-flat earthers that come in here that have been in it for 8 years, 10 years, they still aren't able to still man their own position when it comes to Walter Bisland's calculator or the refractive index or atmospheric refraction itself, right? They can't even define it properly. They screw up the most basic things. It's very rare to get a glober that even knows what they're talking about when they say the word refraction. Most of them have just learned to just kind of say that word and they think it's a get out of jail free card.
I would say even the ones who claim to have a very strong knowledge on refraction don't know very much about refraction. They just know their best position and how to present it. Like they said, okay, this here is how I should try to combat the flat earthers from this vantage point. And so anytime we have a conversation, my whole goal is to never leave this frame, because in this frame I can make them look silly or I can make them look stupid if I just commit to this frame and I dodge all questions or I dodge all detours, because that's ultimately what it comes down to for me. Like when I talk to them, is I feel like I'm being guided, like they're trying to guide me into a particular question that they can jump on me on, because like I don't know everything, but and I don't know what it is they want me to say either. Like they're asking questions, but they're actually looking for they're looking for me to say something, and I don't know what it is. so yeah.
Yeah, they're waiting for that moment to where they can be like, got you. And then they'll try to exploit, like even if you misspeak, they'll try to exploit that, because what they're ultimately doing is, this is just a tactic that they have. They're just trying to find a way to discredit you. That's all they care about. They'll attack you personally once they find like a small little chink in the in the armor. They'll be like, they'll try to exploit that. Like, and it could have been just something simply you just misspoke, and then they'll pounce on that, because it's a tactic.
Yeah.
All those other globers, like in the other servers, like you have like Shoebill and you have the surveyor guys like Shoebill and Omni and all these guys that they think they know about. There's even like some that actually are legit surveyors, but because they stand on that like podium as saying, oh yeah, I'm a surveyor, so then all those globers in that server, like they like bow down to him pretty much, and they go, oh, he must know what he's talking about because he's a surveyor. But then but then that guy will turn around and admit, like, yeah, it's a calculated value. But then I don't know why, for some reason, the globers don't hear him say that. Like, it's really weird. Like, sometimes the guy's honest. Some of those surveyors, they are honest, but then they'll go, oh yeah, but we just add it. I said, yeah, exactly. You change it. So anyways, it's funny.
And they discredit all the guys that are on FE that do have surveying certifications as well. So it's like, oh, you're a flat Earth surveyor, so you don't
count.
You don't count, right?
Yeah, it's crazy, those guys, man.
Yeah, after having conversations with some of these so-called surveyors, a lot of them they're just kind of operators, like entry level survey technicians or something like that. Maybe they did a 6-month course or something, passed a few exams, and now they're on Discord saying that they know everything there is to know about measuring the globe, and surveying. But quite often they'll make really stupid errors, right? Like Jay Reese is one that comes in sometimes, and he was trying to tell me that mirages can't happen over small scales, over small areas. It's impossible. And then I'm showing him ones done over a small scale, like just over a couple of meters. He's like, okay, yeah, well, I concede about that, but it can't happen at mid scale. The distances we're doing over our surveys, it can't happen. And then we showed him some examples, and and then they just try to change the topic, and they a lot of them really don't know what they're talking about when it comes to refraction, miraging, that kind of thing, especially miraging.
Yeah, I've tried to talk to people who tell me they'll straight up say like, oh, we're measuring, we are doing surveys down to the millimeters, folks. With GPS, we are accurate. We are accurate down to the millimeters, and it's like there is a difference, by the way. And I try to tell them this: there is a difference between the precision readout of your instrument and the accuracy of your instrument. Okay, so when they're doing like their GPS measurements, the instruments will read out a precision value. It is a precision value. It's highly precise. Precise meaning reads down to a very low decimal point. But the accuracy of it is quite low. I'll actually just read an abstract from just if you want. It's just one sentence. It's like literally just like one sentence.
Yeah.
From the refractive index of air, new equations for the visible and near infrared. And this was by Philip E. Sidor, I think is actually how you say it, Sidor. And in case you're wondering, this guy came up with the density model for the globe with the assumption of 7/6R built into it. Like this is like a very high up there optictician, if per se. And this is the very beginning of his abstract. It says, the precision of modern length interferometry and geodetic surveying far exceeds the accuracy, which is ultimately limited by the inadequacy of currently used equations for the refractive index of the atmosphere. Right there, the precision of modern length interferometry and geodetic surveying far exceeds the accuracy. And I think that is like understatement of, that's another one of those like right there in competition for understatement of the year. Like seriously, it's up there. So they'll say we are measuring these down to the millimeters, and it's like, yeah, you've got an instrument that will give you a readout to the millimeter, but your accuracy can be off by feet. And if you're going over a long enough area, it's very hard to see that. It's very hard to see that. And almost nobody is doing flat grade surveying at any distance where the difference in height is going to be any more than just a few inches, even on big projects. So, yeah. And no one's going to try to do one continual slope the entire direction. There'll be drainage considerations across certain areas in smaller subsections, because they know if we try to get this all in one long survey where everything sheds one direction, they won't be able to do it. That's why they never do it that way. That's why there's always drainage considerations midway through the project of like, this is where the drainage needs to be here, it needs to be over here. It never works. They're not using a planar model when they're doing it. They're assuming that, oh, this is in fact curving, and it's not.
Have we got that? Can you share that with us? Have we got that, DJ?
Sure.
On Pickle
Sure.
Minds?
Here's just
Nope.
You can't actually. You won't be able to.
I was about to. Go ahead.
Yep. You won't be able to read the whole article unless you pay for it. But here it is. I'm putting it in the side chat of the 24/7 Flat Discord. And here you go.
Thank you.
Should I use all the fruit? It might be.
I mean, that's from 1995. It's like if people in 1995 didn't know how to measure the ground, we're screwed. You know what I mean? The globe's screwed. If they're saying it's that inaccurate in 1995, that's terrible. That's just trash. I mean, that's unacceptable in the current mainstream like idea of we can measure things down to the frickin' millimeter.
And what distance generally are we talking about that he's referring to when he's saying it's inaccurate over X distance?
You would never be able to do it. Then he's not referring to any particular distance in his statement, but what he is saying is usually geodetic surveying is done like on bigger jobs, right? The idea of like using the GPS, it's usually done on like things that are going to be over like 1/10 of a mile, right? in distance or shy of 1/10 of a mile. Like let's say like maybe like a 12th. So that's usually when you stop using the theodolite and you start like strictly just the theodolite and you move on to like a position system. So we're talking about most of the time they're saying they're doing this down to the millimeter. It's like, okay, so like you treated the world basically like it was flat and you're maybe off by an inch. Is anyone going to notice that you're off by an inch? Do you know how hard it is? Well, I'm not posing a question. That's rhetoric, and it's not really a good way to phrase a way to speaking. But it is incredibly difficult to determine if your grade is off by even a single inch across an entire area. I mean, that's very hard to do because how are you going to measure that with a light? Well, the light is the problem, is that it doesn't go in a straight line. So, it's pretty difficult. I'd say the best way, honestly, to get an accurate measurement is to use a water level. But just me.
Right. So if we've got some of these like anti-flat earthers going out making hyper-specific claims using some old theodolite over, say, 50 miles or something like that, right? Peak to peak. That's probably not a very good idea, right?
Well,
Especially
the peak thing is like they're not
Even
accounting.
100.
They're just trying to say, "Hey, look, we're getting above the refractivity of air," and it's like, actually, you're not. You would have to get out of the air because anywhere you are, dependent on the layer, you can have light bending up towards the density above you because there's different layers. Like the Fata Morgana shows this very clearly, that there's different layers going on. And
yeah, absolutely. It's also more common for there to be the warmer pockets of air down lower in the mountains and that kind of thing as well, rather than cooler air down lower and warm air above.
Well, and you got to keep in mind that also it's really like they make these claims, but they never, when they do this theodolite measurement stuff, it's like, well, why don't you, get your surface measurements? And it's really hard for to do it on a mountain. I know this sounds weird, but to actually take a surface measurement from the mountain is really hard because usually a mountain is falling away from you in every direction. So you have this like kind of conal effect happening. You're not using just a flat surface anymore. Now you have to have like, okay, what is the surface temperature maybe at the bottom of the mountain and then also where you are on the mountain as well. So then you can work out how much is being lifted through this funnel in terms of like humidity rise. Like humidity is such a huge factor in this, and they're not taking any of the measurements I've seen from peak to peak. They're never taking it into account. They're never taking any of the environment into account. They just go up there and say, "Ha ha, we went higher than," and it's like, no, you didn't. You're still in air. You can breathe up there. You know that, right? You can breathe up there. So obviously, there's going to be refractive effects going on. It's kind of sad.
Oh yeah,
Cheating I see
you
going
could
on.
you can even just go to Google and type in mirage in mountains or mirage high altitude, and you can see crazy miraging effects, over mountain peaks and things like that.
Oh yeah, because ultimately it's more about the distance. A lot of the times it's about the distance you're looking, and not the overall refractivity of the air. Like on a flat plane, a lot of these mirages make a lot of sense because it's happening over such a long distance. Whereas on a globe, like you guys were saying with the oil rigs, which I'm just going to presume you did your due diligence in that. I mean, you have to have a lot of refraction, like happening all at once, like in a very short span of area. It's pretty silly. And it's not just a little silly, it's really silly. Oh my gosh, look at that. That's a fata right there over a mountaintop. Interesting. What I find interesting about flat Earth is we're over here talking about measurements and the environment, and we're not just like saying but outer space, you know? I mean, we can show things that don't work in the sky too, but we're like more concerned with what the Earth is.
Oh yeah, yeah, and
I really like that
that's
about
hard.
it.
Yeah, absolutely. They'll do whatever they can to try to get the conversation away from that as well, especially in this server. Try to take it back to the sky. Not sure if you've seen this this one, Lanolin. This is my go-to one, really. A lot of people's go-to one when it comes to the Santa Barbara oil platforms. This one was done first thing in the morning. Extremely clear conditions, 8-foot observer height. Full video about it as well, but it's extremely clean.
And first thing in the morning, that's a really awesome time to do observations, and it's because you had all night for the air temperature to stabilize, right? And the surface temperature to stabilize, and you have no third element source heating, right? You don't have the sun adding another heating element to it from above. So you've got a lot more stable environment to work with. So I think that's pretty fascinating. To be fair, that could mean it could end up resulting in downward refraction, or it could end up resulting in slight upward refraction, depending on the air temp, but and the release rate at the time. But it's more than likely this is going to be upward refraction every time, because the air would have to be significantly warmer, like in a very serious way, than the water itself, for condensation to occur.
Yeah. Yeah, we do have another good observation that Indio 007 did. I'm not sure if I showed it to you, but he used infrared P900 or P1000, and he waited for a day where he found the water temperature and the air temperature to be completely identical, and he made the observation right where the buoy is that takes the readings. So he was able to see track a boat on marine radar 10 miles out, just over 10 miles out. He had his camera at 15 foot. And so, yeah, so we had identical water and air temperature, or close enough. And we had a known distance. And yeah, you could see the whole boat. You could also see the whitewash because the boat was moving. So you could see the little waves at the bottom of the boat. Really cool observation.
Yeah, and I would guarantee that I can't guarantee it, but I would say with great certainty that if this isn't in like freezing conditions, your relative humidity probably isn't 100% right at the surface. So, and that is one of the major fictitious impositions they put into the data. Is they'll claim that the surface is experiencing an extreme amount of humidity right at the ground. It's called supersaturation, where the relative humidity right at the surface is at 100%. Even if just above the surface, it's like, and I mean like 5 inches above the surface, you'll have a hydrometer that says like 50% or whatever. They'll be like, oh no, right at the surface it's 100. And the reason why they do that is because if the capacity of air is full, okay, it can't accept water vapor as fast. So it's basically a way to dry out the world, to make the world really, 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 really dry by making the area right above the surface incredibly wet to where it can't actually let any water escape the surface, which is just patently false. We'd have no freaking clouds in the sky if that was the case. So, yeah, it's like it sounds like you're in an environment if the air temperature is almost identical to the air temp. In fact, if you could, I mean, if that is indeed the case and your relative humidity is below 100% at the surface, then yeah, you'd be seeing upward regression.
Yep. I think we have
in that one direction.
Yep.
But you would need a second point to guarantee that.
It was like half a degree warmer water than the air temperature as well. So.
Well, even so, I mean, even if it was a half a degree colder, that's so close. That's so close that just the buoyant thrust itself is lifting the density gradient. That's the whole thing. That's why they have to impose hydrostatic environments or supersaturation, they can't actually let the vapors rise, because even if the vapors are a little bit colder, they're actually still lifting the air. Like, it's a literal thrust. I mean, it's a measurable thrust. More buoyancy underneath thing of higher density causes density lift. So it's a displacement upward. That's why they can't have it rise. I mean, they basically have to say when I would say their primary point of contention is at the beginning of the Bible. It says, and then God created the dew. You know, like the dew came up from the ground, and it's like, oh no, we can't have something God created in our system. We have to make it go away. There's no dew. There's no water coming up from the ground.
Yeah, it's a great point. It's actually a point that I never really considered. So here's the observation I was just talking about, just a GIF of it in the side chat, along with the information from the buoy, which is basically at the exact same time that he did the observation as well, just before. So water temperature 45.9, air temperature 45. It has a bunch of information about the dew point and all sorts of things there as well.